Who's after me?
It's on the presentation.
Lars,
What's Lars teaching?
the intro to mic.
There's no lab for that one right now.
No, it's just a 30-minute overview. This one,
I think they have 2 lights left.
infinite windows, and John Kaz's PDF.
So when you hit that screen share link, it gives you an option of different screens to select.
Always go full screen or full desktop. You can start whenever you are ready. And Carlos is being back, waiting for his time. He goes to 9:30.
You just said Lars.
Lars goes to 30 minutes.
Oh, okay. Carlos goes next.
No, Lars goes next.
Okay.
Lars, Carlos.
Good morning, everyone. I'll go ahead and get started, and people will trickle in. I'm going to give an overview of the hardware we have here at TACC. I know the title is HPC hardware. Should probably be more like TACC resources. There's a couple of items in here that aren't for HPC. My name is John Kaz. I'm part of the HPC group here at TACC. Just a quick outline of the systems I'm going to cover. You should have been introduced to Stampede yesterday for your labs, and I'll talk about a few of our other systems. Okay, so you may wonder, well, why do we care so much about hardware? In the good old days, you could just write your program, compile it, and wait for the new processor to come out, and things would get faster. Well, that's not how it works anymore. The processors don't usually get that much faster. They have more cores, they have better memory bandwidth, or they have other features. Well, so now when you program, if you want performance, you need to program towards these hardware features, and you need to be cognizant of them so you know how to write your code in a way in which you're using them efficiently. And so that's why we're going to give a very quick and dirty overview of what hardware we have, and then later on at the end of the day, I think someone will touch upon optimization and how to profile on this hardware so you can begin to tune your code to work effectively. Just a little note about maybe the difference between our center and, say, a center that someone like Yahoo or Google or Facebook might have. So we're a high-performance computing center. We run many applications that run very tightly coupled on multiple servers, where at a data center, most of the applications are designed for data throughput, data processing, and they're not so tightly coupled. In other words, if I do a Google search, I don't care which server gives me an answer, I just want the quickest answer. So it could be that multiple servers provide a result, and they don't know that the other servers are doing this, so they're not very coordinated. Although, as progress marches on, data becomes more and more important, and so we're beginning to look at systems and bring in systems that are more in the flavor of, say, something that Google or Yahoo would use, because these HPC systems are creating such large amounts of data, and new projects for observation are creating large amounts of data, like the Digital Sky Survey and Dark Energy Survey and LIGO, that we need these large data processing systems to do the data analytics. Okay, so the first system I'm going to talk about is Lone Star. This is our oldest system. This will probably be the last presentation where we discuss this version of Lone Star, because it's scheduled to go offline at the end of December. And so right now, what we're doing is we're letting people finish out their allocations, and we're still supporting our partners from the University of Texas Systems, Texas Tech, and Texas A&M. So this was a system that we installed in late 2010, and it came online in early 2011. It was a $9 million system with money from NSF, from the University of Texas, Texas A&M, Texas Tech. I'm probably forgetting another partner. It was a consortium that we put together to fund this system for a lot of local research. And it's been a great system. It's a workhorse. But 3.5 years in HPC is ancient. So it's time for it to be retired. Just a little bit of the details on what's on the system. There are 6-core chips. It's connected by InfiniBand. We have some special nodes. We have some large memory nodes for people who need just a large amount of memory, maybe not so much parallel processing, and some GPU nodes for visualization and data analysis. Just a very quick look at how it's set up. It's a blade system, and I don't know if you've had a tour yet, or if you're going to, you should have a tour, but you'll see a similar setup in our system across the hall, Stampede. I'm going to talk about it in a second. And so what this is in general, there is a chassis put into a rack and blades put into the chassis. What I want you to notice here, well, I'll use the mouse because so everyone online can see. Notice how these racks look a little empty. There's a lot of space at the top and space in between the chassis. This is because they create so much heat and such a small footprint that we could not fill the rack completely up because it would overheat the room too much. And so we purposely have the racks a little bit empty so that our power density is such that we can cool it. Just a quick look at what kind of file system we have on this system. And this is very similar to our other systems in that on all of our HPC systems we have a home file system, we have a work file system, we have a scratch file system. This may have been covered yesterday, but home's backed up. It's where you keep your important stuff. Work is not backed up, but it's not purged, and you have a quota, so that's where you sort of keep your intermediate files. And scratch is where you run. That area is purged, but that's where you want to do all your I/O, especially if you have high I/O bandwidth needs, because that's designed to support the largest amount of I/O. Okay, so now I'll move on to Stampede. This is our crown jewel. This is our largest system, the most powerful system we've ever had at TACC. It came online about 1.5 years ago, January of 2013, and it's a system right across the hall, on the other side of those windows. It was funded by an NSF solicitation. It's primarily used to support XSEDE users. We have a small portion of it set aside to support University of Texas directly. And one of the differences about this system and other HPC systems that were previously solicited by NSF is it had to have a key innovative component. I'll talk about that in a second. It was a partnership with Dell and Intel. We designed the system with Dell and Intel, and it was quite a long process. It probably took us about 1.5 years to design this, and then it took about 9 months to install the whole system and get it up and running. And yes?
What did the prospective partners contribute to the collaboration partnership? Did Dell contribute equipment? Did Intel customize?
Well, so Dell's the vendor. So, I mean, Dell got paid to build the system, but Intel and Dell worked with TACC to do the design of the nodes and how we would set up the Xeon Phis in the nodes and design the chassis in the rack and sort of the overall system design. So they contributed in many ways.
Did they commercialize it?
Yes, they go try to sell this system to other people too. Okay. And the innovative component is the mic. And so as I speak, you might hear me say mic, you might hear me say Xeon Phi, I might say something like KNC. It has many names. Intel decided right about when Stampede went online that the commercial name should be Xeon Phi, so that's Intel's name for it. The whole architecture is called the mic, many integrated cores, and Intel's code name was Knight's Corner. So if you hear any of those words, I mean the same thing. I try to be consistent, but I'm not. So before we could install this system, we had to greatly expand our machine room. And where you're sitting now is just to the is right here, just to the north of the machine room. Originally, this was all parking lot. We didn't have space to put it in our old machine room. We had plans to expand our machine room, but then once this solicitation came through, it got put on a fast track, and basically this whole building was completed in about a year. And so you can see here, this was our old machine room and our old system Ranger. It's a bit smaller. If they give you a tour, you should get to walk through that section of the machine room too and see there's a lot of empty space in between some coolers, some in-row coolers. Okay, so that's not even the largest construction project. The machine room was just part of it. To power and cool this new system, we had to build a whole new power and cooling facility. And so UT built us this nice system right here that does cooling and power. And we pump about 3,000 gallons per minute of chilled water into this machine room to cool these systems. And we added 6.5 megawatts of power to support this system. Now, Stampede, I think at its peak will use 4.5 megawatts. Right now, just running regular jobs is probably using about 3. But we've got the capability to support 6.5 megawatts. It's just a layout of the machine floor. This is just to give you an idea how big it is. They take you into the machine room, you'll see this. One of the few things I want to point out is all these yellow boxes, those are the switches. So there are 8 switch cabinets. Every node is connected to every switch. This is what gives us our bandwidth and connectivity. The other thing I'd like you to notice, all the blue squares are the compute racks. That's where all the compute is. So you may wonder, what are these little green things here? It says IRC. That's an in-row cooler. So what that basically is a little air conditioner that sits between each rack. We have hot aisles and we have cold aisles. So on the hot aisle, the hot air comes up into the aisle and it has a little ceiling to contain the hot air. And then these in-row coolers suck the hot air through to the cold aisle and chill it. So this is why when you look at a Stampede node, it's full of nodes. It's filled all the way up, where the Lone Star nodes were kind of empty. It's because we have these in-row coolers to provide extra cooling capacity. So when you go in there, it'll be kind of cool on the cold aisles. If you go down a hot aisle, it still won't be that hot because this works so well. Basically what I just said. I'll mention the last item there about the mineral oil cooling. We have a partnership with a company called Green Revolution, and we have a couple of containers which are similar to a rack in which you can put computing equipment into mineral oil. So the advantage of cooling with mineral oil is it has a much higher heat capacity, so the mineral oil only has to get down to about 100 degrees Fahrenheit because that's still cooler than the chip, and it can keep the chip cool enough to run. So it's much cheaper to cool things with mineral oil, although I'll tell you it's a lot messier. Here's a picture of the infrastructure that they built. So what you see over here, this is the pump room. See all the pipes? There are 3 pumps. There's usually 2 pumps running and 1 pump down for maintenance and also a standby. This is slow mouse. The power room, a lot of the breaker switches and the transformers. Here are the chillers. You may be wondering what's this in the middle, this strange looking room. That's the inside of this tank over here to the left. So when we built this new cooling facility, to save money on power, what they did is they also built this huge insulated tank. So overnight, what happens is the chillers chill more water than is needed and pump it into the tank. During the hottest part of the day, from about noon to 4 or 5, the chillers should cut off. And the chilled water we use is what comes from that tank. Because this is also the time of day when electricity is the most expensive. Okay, so now I'll finally get to Stampede system. I was speaking about the infrastructure. When Stampede first came out, it debuted at number 7 on the top 500 list. Anybody in here know what the top 500 list is? Okay, one person. So that's a ranking of HPC systems around the world that runs one benchmark called High Performance LinPack, which is basically just a big DGM benchmark, a big matrix multiply. And we came in at number 7, and now I think we're hanging on at number 10 a year and a half later. So Stampede was quite a bit more than Lone Star, but it's quite a much larger system, $27.5 million to support it for, I think, 4 years of running, and there's an extra funding to support operations and maintenance. So it says here it's 9 plus petaflops. I think we're actually over 10 now with one of the upgrades. It's based on a 2 petaflop general Linux cluster. So if you don't look at the mics at all, it's a little over 2 petaflops. When you add the mics in, that adds another 8 petaflops of performance. And I'll get into the details of the chip and the mics in a little bit. As with Lone Star, we also have 16 large memory nodes for people who need a terabyte of memory on one shared system. 128 GPU nodes. What's really nice about the GPU nodes on Stampede is if you're writing a program that, or if you already have a program that supports GPUs, and you want to write a program that runs on the mic, and you want to compare them, on all of our GPU nodes, we have both a GPU and a mic, so you can actually run and compare on the same node. So here, I'll talk a little bit about the processors. So on the regular Linux host side, we have Sandy Bridge processors, dual socket, 8 cores apiece. It's basically what you find on any other Linux cluster. Well, that was built about a year and a half ago. If you get one now, it'll probably have Haswell if it's new, or Ivy Bridge if it was built in the last year. The Xeon Phi is the innovative component. So this is a card plugged into the PCI slot that has 61 cores. It also has what's called hardware threads, so it's similar to hyperthreading. So each core actually appears to the system as 4 cores. There are actually 244 cores available. And so I just want you to take a look at these processor specs, and this is where what I said earlier about high performance and hardware, how the hardware matters. How you optimize for the mic, it takes quite a bit more effort to get to run well on the mic than on the regular Sandy Bridge. The biggest advantage, though, is just about everything you do to make a code run faster on the mic translates directly to the Sandy Bridge. So your code will run faster there. But it's much easier to optimize for the Sandy Bridge because it's a more sophisticated processor. On the mic, it's a less sophisticated processor, has a bigger vector unit, but there's many, many more. And I think right after me, someone's going to give you an intro to the mic, so they'll go into more detail about this. Well, I'll have some mic details. Basically, what it is, it's a stripped-down x86 core. Some people have called it, I think, like a Pentium 3. So a card full of Pentium 3s with a really large vector unit. And so when you program for it, you basically have to understand that some of the things you expect in a chip, like out-of-order execution and look-ahead, are not on this chip. So your program sort of has to be simpler and more straightforward and concentrate on vectorization and multi-threaded parallelism. The nice thing about the mic that's different from the GPU, you can actually log into it. It runs an OS. I won't say a full OS because not everything's there, but it does run a Linux OS. So you can actually log into the mic and just run things in a native mode. Where with a GPU, everything you do is offloaded in a kernel. This is just a quick look at the architecture. The main thing to notice here is all the cores are connected in a ring network. So what this means is even though when you log into the mic it looks like one system, let's say you have instructions running here and instructions running here. If you're running a shared memory code, and let's say thread 1 wants to talk to another thread, depending on where they are on this ring, there's more latency as to how it can access the memory of another thread. So in general, when you run on the mic multi-threaded, you want to lay the threads out so they're close to each other, so they can share cache or be close to each other on the ring. And so each node is composed of 2 standard bridge processors, yes. The cache. So there's an L1 and L2 cache for each core, and they're all snooped, right? So every core can see the other core's cache. There's no L3. There's main memory, that's it. And so each node has 2 regular processors, 2 standard bridge processors, and 1 or 2 mics. Every node has at least 1 mic. We have a subset of nodes that have 2 mics per node, and there's a special queue for those. And the other thing you need to worry about when you're programming to, say, run on both the mic and the host, one of the biggest differences is there's 32 gigs of memory available to the host, but there's only 8 gigs of memory available to the mic. So this is just another imbalance you have to worry about. So let's say I make the mic really fast. Well, I've only got 8 gigs of data to operate on. I've got 32 gigs of data on the host. So then I have to worry about moving data across a PCI bus from host to mic and back. Just a quick look at the configuration. As you can see, the mics are only connected to the host through the PCI bus. Now the next generation of mic, the Knights Landing, it will be able to exist as a self-hosted node. So you would have a node that only has a mic chip, rather than just a mic chip on a card attached to a regular host. But that won't be out until I think late next year, early 2016. Okay, as with our other system, we have 3 major file systems: home, work, and scratch. Now here, work is a little different. Lone Star is an old system, so its work file system is local. For Stampede and the next system I'm going to show you, Maverick, the work file system is shared between them. It's not local to the system. But what this allowed us to do is create a larger work file system with a larger quota. And also an easy way for you to share files between systems. Because each system has work mounted and you can just copy it to Scratch or wherever you need your files. Also, the parallel file systems are all Lustre. So Lustre's a high performance parallel file system, but it's also one that's a bit touchy. So if you use Lustre at large scale in a bad way, you can do things that will impact the file system or could crash the file system. And so if you want to scale up and do large scale I/O, please submit a ticket and ask for help first. Because when you're programming on your laptop, you usually don't think about I/O, just do it. You get on one of these large systems, that works up until about 1,000 tasks. Then maybe you'll have to change your I/O scheme. And if you don't think about it or do it correctly, you can do it in such a way that greatly impacts the file system. You might get a note from an admin saying, hey, I turned you off. You can't do that. But don't worry if you do. Just submit a ticket and say, hey, I did something wrong. I don't know what I did. Somebody help me. And we will. We do this all the time. And maybe a little bit of explanation about these OSSs, OSTs, MDSs. And MDS is the metadata server. This is one of the reasons Lustre can have a problem, because every initial I/O operation on Lustre has to go through this one metadata server. We have a backup. That's why I have 2 for this one and 4 for that one. So there's one that can fail over to. But so this is like the traffic cop of the file system. And if there are too many I/O operations in a short amount of time, it gets overloaded. Things back up. And these OSTs, that should be OSTs, that's like the number of RAIDs on the back end. So the more OSTs that a file system has, usually the larger the file system and the more parallel bandwidth to the file system. And just a little bit about what each file system is on Stampede. The main thing you should be concerned about are quotas and purge policies and backup policies. As I said before, home is backed up, but you have a fairly small quota. Work, you have a large quota. Actually, I need to change this because our work file system now has a 1 terabyte quota. So you have quite a bit of space on work, but it's not backed up. So anything that you really need on work, if it doesn't fit on home, you should put it on one of our archive systems. And Scratch, this is where you should, in general, do your computing. When you're doing I/O for your parallel runs, you should be reading and writing from Scratch. Now, Scratch is not backed up, and it's purged. The purge policy is 10 days of, after 10 days of no access. It doesn't have to be updated. If you regularly access your files in Scratch, they won't be purged. But if it goes more than 10 days without anything touching it, it can be purged. Doesn't mean it will be. So we pretty much run purge when we need to. So I'm just saying, if you leave something there and it's there for 2 months, don't expect it to be there forever because it still might get purged. Oh, and also /temp. You should be aware that on every node on Stampede there is a local disk, and so there is a local directory that you can use. Now the advantage here is some codes don't need a parallel file system, and they do I/O in ways that would impact a parallel file system. So for these users, a lot of times we tell them, look, during your workflow, just use /temp, and then when you're done, copy all the results you need back to the parallel file system, because /temp gets erased at the end of your job, or cleaned out. So also on Stampede, we have 16 large memory nodes, as I mentioned before, and 128 viz nodes. And the large memory nodes are in quite high demand. Not a lot of places you can get a node with a terabyte of memory. So just a quick look at the queue structure on Stampede. In general, most of you will probably run in development or normal. If you need one of the specialty nodes, there's large mem, viz, and GPU. There's a little bit of difference between viz and GPU dev and viz dev, and it has to do with which libraries are loaded, X11 libraries, no X11 libraries, which features are added. And then if you need to do any computing with the mic, you should use development to develop your code, but once you start running, you can run a normal mic or this normal 2 mic. Normal 2 mic is a queue where there are 2 mics per node. Okay, so that's Stampede. I'm going to move on to Maverick. That's our newest system. It was just installed earlier this year. Unlike our other systems, which if you notice were all Dell, this is an HP system, so that's a nice change. It's primarily for visualization, and it's set up and configured to encourage interactive visualization. It's 132 nodes. Each node has a, I don't think I have it on here, but no, there it is. Each node has a NVIDIA K40 GPU, which I think is the latest GPU from NVIDIA. And as with our other systems, it's connected with InfiniBand. It runs a Lustre file system. It has a Slurm scheduler. Like I said, it's primarily for visualization, remote and interactive, and the queues are set up to give that priority. We do have lots of people who run GPU jobs on it just to do computing. They're limited to 12 hours, and they have lower priority. And this last statement about the higher memory requirements. We have a special queue for special requests for anybody who needs to run outside of 12 hours and either needs the GPUs or the larger memory per node. This has more memory per node than the other systems. But special request also means short term, as in we'll put you in this queue for maybe a week. at most a month, and then we'll take you out. Also, all our systems have visualization software. So since we have GPU nodes for Lone Star, Stampede, or Mavericks, all GPUs, this is available on all the systems. I've used Visit and ParaView. I haven't really used Vapor, Insider, or Mira. But if you have questions about these, just let us know, and we can direct you to the Viz staff, and someone can answer your questions. I thought I had another slide on software, but maybe not. Okay, storage. So these are definitely not HPC systems. Please don't compute on them. Don't compile or run anything on them. Just access these systems to get to your data. So Ranch is our large archive system, which is backed by tape silos. We have 2 huge tape silos to store all the data on Ranch. 40 petabytes. I think we're about half full now. I'm not sure. But the thing to know about Ranch is you put your data, you log into Ranch, it looks like a regular file system. Okay? You LS, you see a file. You go to access that file, or let's say you go to copy that file off and it takes forever. Well, what's happening is if the file sat there for any amount of time, maybe a few hours, it's been archived to disk. I mean to tape. And once the file is archived to tape, there's usually nothing left on the disk except a header or a stub, maybe a little bit of the data. So what happens is when you go to move that file somewhere else, the system has to restore it from tape. You can do this manually with a stage command, or you can just access it and the system will do it automatically under the covers. But it may take a while. It shouldn't take a long, long while, but it may take a few minutes before it's restored that file or files back to disk. Then after the files are completely on disk, then they'll transfer all. So if you do an SCP or an rsync or something. But I'm just saying, be patient with Ranch. Now, if it looks like it's taken a half hour or longer, you can submit a ticket because probably something's wrong. And in general, what's wrong is someone's trying to restore hundreds of terabytes of data and the system's congested. I think we have 16 tape drives for Ranch, and yeah, sometimes they're all in use. And if you notice, this disk cache, 640 terabytes compared to 40 petabytes of tape, that's not the best ratio. We need to pump that number up. Because sometimes that disk cache fills up. And so then Ranch is trying to restore data and archive off old data, and it just gets congested. And the admins sort of step in and halt some things and push other things along and have to act like a manual traffic cop. Our other archive system, Corral, this is sort of for intermediate storage. Let's say I need to park a database somewhere that I'm going to be accessing, or I have data that maybe I'm going to use a few weeks from now, but I can't keep it on scratch, but I am going to be accessing it in a fairly quick manner, so I don't want to put it on Ranch. So Corral's where you'd put this. The thing is, Corral is not allocated by XSEDE, so this is only available to University of Texas system users. And the last slide, or next to the last slide, is a bunch of references for the user guides. Yes?
So, budget is allocation for Corral?
So for Corral, it's allocated through TACC. So if you want an allocation on Corral, you can submit a ticket to TACC and ask for the allocation, but someone on the project needs to be related to the University of Texas, maybe any Texas university. I'm not sure how broad Corral is, but it's not allocated through XSEDE. Oops. So yeah, the last slide's just our user guide references, and one at the bottom for the Xeon Phi on Intel's website. My name's John, and if you have any questions, send me an email. Thanks. Okay.
this is all in one. Oh, you are downloading it directly from the
Sure.
thingy.
Yeah.
Good. Oops, it says XSEDE. Didn't fix that.
Let me change it. Oh, it's a PDF, so. Let me save it to the desktop.
Is it the one lecture? What's this one?
That's it right there.
No, you have to go to.
No, this one.
No. You have to go to full screen. No, where is it? Full screen. Okay, thank you. Is this the? You don't have a pointer?
No, just do that.
No, I mean a laser pointer.
No.
Okay. Okay. My name is Lars Kostak. I'm also here working at TACC, part of the HPC team, and I'm going to give you in a Xeon Phi overview. I apologize. I changed my name, but I didn't change the venue. So these are the slides that we used a couple of weeks ago, 3 weeks ago at the XSEDE 14 conference. Okay, so we are giving a whole day lecture on the Xeon Phi as a standalone module that we teach. So this overview will be very, very brief. It's actually only 30 minutes. It will just give you a rough idea of what the Xeon Phi is and why we think it is important. And I want to highlight that our machine out there, Stampede, has 6,400 nodes, and all nodes have one Xeon Phi, and I think 480 nodes have 2 Xeon Phis. So in total, we have 6,880 Xeon Phis in this machine. So we think it is a technology that is very promising and that can speed up user code quite a lot. So Xeon Phi, also known as Mike, that's the first product from Intel in this many integrated core line. So Mike stands for many integrated cores. That's the name of the architecture, and Xeon Phi is the name of the first product. And it is Intel says it is a CoProcessor. It is a PCI Express card that you put in your desktop, or you put it in the nodes of your supercomputer, like we did. And on that PCI Express card, on that Xeon Phi, there's a Linux operating system running. It is very much stripped down because, as you will see, there are some memory limitations on this card. But it is, once you have powered it up, basically a computer within the computer. So you have a Stampede node, you can log on to the node, and once you're on the node, you can also log on to the card. And so it's a little bit different than a GPU, which is a device you cannot log on to and where there is no Linux operating system. But we get to some of these details in a minute. It is a very dense and slightly simplified processor. So the goal is to take a huge chunk of silicon, a big chip, and put only stuff on there that gets you through some computational intensive, some number crunching code. So it is very dense. It means it has many cores, like the name already says it, many integrated cores. And then some of the complex hardware that you find in the Xeon, in the CPU chip, those are removed to make room for more cores that are put on this chip. And at the same time, to increase floating point throughput, it has a wider vector unit and it has more threads than you will find on a Xeon. And the last bullet point here is just to unconfuse you about all these names that you hear. Mike is the name of the architecture, many integrated core. Intel Xeon Phi here, the last line, that is the processor name, and then this SE10P, that is the specific version of this Intel Xeon Phi. And the code name for this product was or is Knight's Corner, so that's also a name that we sometimes use. Okay, so Intel is a big x86 shop, so they only do x86, and so it's not surprising that they built this accelerator or coprocessor also based on x86 architecture. And by doing so, they've created something that looks very much like a CPU, but it has just more cores than you find on your host. And the cores are a little bit simpler, and they allow for more compute throughput. So now, one of the advantages of having a coprocessor, an accelerator that is very much alike to your host, is that you can use all the programming models that are used on the host also on this coprocessor. As I said, they dedicate as much of the silicon to floating point operations, and it's a device. Our devices, they have 61 cores, so there's a lot of cores on this chip. But nevertheless, Intel was able to maintain the cache coherency protocol. So when all these cores interact with each other, then there's a cache coherency protocol that keeps all the data that is stored in these cores and on all the caches attached to the core in a coherent state. And by doing so, that is one of the key elements that was needed so that you can leverage all the existing x86 programming models without any or many modifications. And so an example is in OpenMP, you have multiple threads and they all access the same data. If there wasn't a cache coherency protocol, you couldn't use OpenMP threads to run on multiple cores of your device. And if you look at an GPU, there is no cache coherency there, and therefore you need a different kind of threads, and that's why, for example, you have to use CUDA if you program for NVIDIA GPUs, or you use something like OpenCL. But here, there's cache coherency, so you can use what you know from the host, also in particular OpenMP. And we will see that using threads on the device is very, very important. So you cannot just run only MPI tasks on that card, but we get to that in a minute. Increased floating point throughput and some expensive features, and expensive in terms of energy consumption on the chip have been reduced or stripped. So these are in-order cores, so there's no out-of-order execution, and the branch prediction, for example, is simpler than the branch prediction on the Xeon. And then you have a wider SIMD registers. Those are these vector registers that you can use to get more throughput, and they have a wider vector unit in these cores. And then on this board, you have fast memory, fast GDDR5 memory that you would also find on a GPU. And our cards have 8 GB of memory. So whatever you have to do on the card, it has to fit into this 8 GB of memory. You cannot use any more than that. Yeah, here's a picture of the chip. So you see a regular pattern. Those are all the cores, and what you see here in the irregular patterns here in the middle, those are memory controllers and other things that are needed to keep the chip up and running. It is based on the 22 nanometer process, so that is Intel's latest fabrication. Those are the smallest. That's the smallest that Intel can do right now, and the chip is coming out of these previous projects that you may have heard about, the Larrabee, the single cloud chip, and the teraflop research chip. And so whatever Intel learned in these projects was then used to build the Xeon phone. And here is a block diagram of the mic architecture. So in green, you have all the cores, And in our system, we have 61 of those. And each core has a cache. That's the one in blue. So to each core, there's a cache attached, a level 1 and level 2 cache, very similar to a Xeon architecture. And then all the caches and all the cores are connected through a ring network that connects all these cores. And then you have, of course, other things like memory controllers and the connection to the PCI Express bus and so on, and so on. But this looks very much like a Xeon chip, but there's no level 3 cache, and there's a ring that connects all the cores. And each core has its own level 1 and level 2 cache. And here's a diagram of the Knights corner core, and here I want to point out that it really looks very, very much like the Xeon architecture. So you have a level 2 cache, 512 kilobytes. You have a level 1 code cache. You have a level 1 data cache, and then there are also TLBs, level 1 and level 2. And you can see that you have 2 pipelines, pipeline 0 and pipeline 1. And in pipeline 0, you can schedule. At a given clock tick, 1 or 2 instructions may be scheduled from both of these pipelines. And pipeline 0 can schedule a vector instruction. But it can only schedule a vector instruction every other cycle. So you may have instructions scheduled every cycle, 1 or 2 from the 2 pipelines, but only every other cycle. Pipeline 0, that's the only one that is connected to the vector, can issue a vector instruction. And that will be important when we talk about the number of threads. So on, here in the upper left corner, you can see that you have 4 hardware threads that can run on the core. And the number of 4 you can motivate by the following. On a Xeon, on a host, you have something like hyperthreading. So you have 2 threads that are running on the same core. If one thread is stalled by accessing memory or doing something and has to wait, then the other thread can jump in and do some computing. And here we are doing the same. But the throughput, the operations that we do, those are vector instructions. Those are vector calculations where you do an add or a multiply. And since a single thread can only schedule a vector instruction every other cycle, you need already 2 threads to get a vector instruction every cycle, and then you add or multiply it by a factor of 2, so you get some concept that is very similar to hyperthreading and comparable to the host. But here you have to keep in mind that you can use up to 4 threads on each core, and you need at least 2 threads to get to the theoretical peak so that you can issue one of these vector instructions every cycle. And that is basically what you want to do to get the best performance. And so I told you already that our devices have 61 cores, and you have up to 4 threads per core. So you will have up to 244 threads on a mic card, and that is a much higher number than the number of threads you will have on the host. Stampede has 16 cores on the host, so the maximum number you typically run is 16 threads on that, because hyperthreading is turned off on the host. Here is a diagram of the vector processing unit. And the important part is here the vector arithmetic. So it is 512-bit wide, so you can store 8 double precision numbers or 16 single precision numbers in one in a vector register, and then you put a different number, you put different input in a different vector register, and then you can do a fused multiply add. So by one instruction, through one vector instruction, you may get up to 16 double precision operations. You have 8 numbers in the first vector, 8 numbers in the second vector, 8 numbers in the third vector, and then you do a fuse, multiply, add. So you get 8 results from a multiply and an add. And if you do single precision, of course, then you get twice the throughput. So the processor, the main reason why companies build these accelerators or coprocessors is to conserve power. If we want to build an exascale system with normal Xeons, we would need a full-size power plant of 1 gigawatt to power a system like Stampede, like the base cluster, the Xeons, and if you scale that up from 2 petaflops to 1 exaflop or 1,000 petaflop, then your power bill would go through the roof. So the reason why these companies are building these devices is not to make our life nicer or the programming easier, because that would be all much more complicated. It is to conserve power. And the main tool to conserve power is that you reduce the clock speed dramatically. You go from here, in this case, from roughly 3 gigahertz, that's the typical clock speed that you find in your Xeons. Here we are going to 1 gigahertz, because the power consumption goes non-linearly with the clock speed. Then you have 61 cores. They have 512 microvector units, which is twice as wide as what you find in Sandy Bridge or Ivy Bridge. And if you multiply out all these numbers, you get some peak performance that is just a little bit north of 1 teraflop. So every device that we have in Stampede provides 1 teraflop of peak double precision performance. And we have roughly 6,800 of those, so you can see where the 7.5 petaflops come from. The data caches are, level 1 is 32 kilobyte per core, and level 2 is 512 kilobytes per core. The memory on the card is 8 gigabytes of this fast GDDR5 RAM, and you can have 5.5 gigatransitions per second from the memory to the cores in the card. And if you transfer, at some point you have to always transfer data from the host or back to the host, and that is done through the PCI Express bus, and then you get 5 gigatransitions at the 16-bit width. Okay, so if you're familiar with a GPU programming, you know that there's a different kind of hardware, different kind of threads, so you learn a new language, CUDA, and that's how you get started. But here with this mic architecture, because everything is x86, you can, the programming for the mic is very similar to the programming for the CPU. The big difference is that optimizing your code is much, much more important on the mic than on the host itself. So this x86, which means it's x86 cores with caches and cache coherency. Mainly, that means that you can use the normal threads that you're used to, the normal OpenMP thread. You have a SIMD instruction set that is for the vector units, and that instruction set is very, very similar to what you know on the host. So everything is very similar when you program for it. So you can stick to the languages that you know, C and C++ on one hand and Fortran on the other hand. And for your parallel computing, you stick to the 2 programming models that also most of our users are familiar with, which is OpenMP, that is for the threads on the device, and then MPI, that is to connect or to do the data transfer from one node to another node. And here, that's also a difference compared to a GPU. You can run a complete MPI task on the mic. So when you start your MPI tasks on a cluster, you can put complete MPI tasks on the coprocessor, which means you can run your complete code with I/O and everything on the coprocessor. And that means that in some cases you are not forced to identify kernels in your code, and you only run those kernels on the Xeon Phi. And those kernels, that would be the technique that you use when you program for GPUs. But here you have a little bit more flexibility. I'm not saying that running MPI tasks on the coprocessor is always a good option. It's kind of the other way around. For very few codes, or for few codes, that will apply. But at least you have the choice of trying that out and see what the performance is. Because the architecture is so much the same and the programming is so much the same, when you run your code on the mic and you will find that the performance is not what you would hope for, and then you start optimizing your code for the mic, anything that you do to increase the speed on the mic will, in all likelihood, also increase the speed on the CPU. So you take your code, you find out, hey, these are my bottlenecks. You optimize your code, you get a better speed on the mic, but you get also better speed on the host. And so we frequently experience or have users that tell us, oh yeah, I tried and played around with the Xeon Phi, my code wasn't really very good, it wasn't very fast, and then I applied some optimization, and that also doubled my performance on the host. So that is not really uncommon. So Stampede programming model. So on a traditional cluster, if you don't have accelerators or coprocessors, you just have your x86 cluster or any other cluster architecture, then you may program it with or run on that cluster pure MPI code, which typically means is that if you have 16 cores in a host, then you run 16 MPI tasks on each host, and then through MPI you do the communication. But you can also do what is called hybrid programming or hybrid execution, where you do MPI plus X, and the X stands for something that is a thread-based or represents a thread-based programming model, which is a very often OpenMP, but it could be thread building blocks or SIP plus or OpenCL or something like that. But on a traditional cluster, there is 2 GB of memory per core on our TACC systems. So it's at least 2 GB per core, and so you can afford to run a single MPI task on each core, and you don't need threads. But on a Xeon Phi, that will be different. Let me come to that in a minute. Now there are 3 usage models for the Xeon Phi. The first one is to run your code natively on the Phi, so you do not care about the host or any other card. You just take your Xeon Phi as a standalone computer. You log on to that Xeon Phi, and then you punch a.out or IB run a.out, something like that, so you can run your code directly, which is very nice when you start playing around with the Xeon Phi and you just want to know how fast is my code, or how fast are some of the hotspots in my code. You can just make a small representative example that fits on a single card. You log on to the card, you run it, you run your MPI code there, or you run your OpenMP code. But in the end, you want to use more than one node, and you want to use the hosts and the Xeon Phi. So we come to the other programming models. The first one, and a little bit easier to realize, is that you have MPI tasks on the host and you have MPI tasks on the Phi. And by doing so, all your communication between host and Phi is going through the MPI calls that you have already in your code. So you don't have to reinvent another communication layer in your code. So that way you avoid some rewriting of your code. So I said on the host you can run 16 MPI tasks without a problem, because you have 32 GB of memory, 16 cores, which allows you to have 2 GB per MPI task. But on the Phi it's different. You have 60 cores, but you have, in quotes, only 8 GB of memory. So if you would have 60 MPI tasks, 1 per core, then that would mean that the available memory for each task is of the order of 100 megabytes, which is typically way too small for most applications. And then keep in mind, you need kind of 2 things, 2 tasks or 2 threads running on each core to get the peak performance. So you're not only needing 60 MPI tasks, but you need 120 or 180 or 240. And at that point, the available memory becomes so small that you cannot, in almost all cases, not run just MPI tasks on the Xeon Phi. And to get around this memory bottleneck, you have to add the threads. Because if you have a thread-based programming model, then most of your data is stored in some shared data, in some shared variables, shared data structure, so you don't have to replicate all your data. And then each thread has a little bit of private memory. And that's why you need MPI plus X, as shown up there, when you code for the Xeon Phi. And the last programming model is the offload programming model, and that is very similar to a GPU programming model. You identify the regions where you spend most of your time and where parallel work is done, and then you offload those regions onto the Xeon Phi. So your code is running on the host, it comes to this region where you do parallel work and a lot of it, and then you offload that to the Xeon Phi card. So in GPU speak, you launch a kernel on the GPU, and in Xeon Phi speak, you offload a parallel work to the Xeon Phi. And what this mostly means is that if you have an OpenMP code, you offload OpenMP parallel sections to the Xeon Phi.
So in the previous model, what is it that you not so you say mostly like 100 volts, so how these are that you cannot?
No, you can run everything, but some things will be extremely slow, like, for example, I/O. I/O has to be funneled through the PCI Express bus and all that kind of stuff, so that's where the mostly comes from. The other mostly comes from, if you had a code that uses very, very little memory per MPI task, you could run 240 MPI tasks on a single card. And that has sometimes even good performance. But imagine now you are on a cluster and you want to use 2 cards. Now you would have 240 MPI tasks on one card and 200 MPI tasks on the other card. And that communication of 240 by 240 through the PCI Express bus and the network, that usually does not work. So that's another reason why you have to limit the number of MPI tasks. So technically you can run everything, but since we are after performance, you bump into limitations there. Yeah, so offloading, you have OpenMP regions, you offload those to the Xeon Phi, or if you use a lot of MKL routines, then you can do something that is called automatic offloading. So MKL is the math library from Intel, and this math library is aware of the Xeon Phi hardware. And when you have a DGEM call where you do a matrix-matrix multiply, at runtime, the runtime can figure out, is it worthwhile doing this matrix-matrix multiply on the CoProcessor or not. So for small matrices, it will not be worthwhile, and for large matrices, it will ship the matrices over, do all these operations, and then ship the result back. So if you do a lot of MKL, you can try your luck with the automatic offloading. Okay, so the Stampede is pretty much a traditional cluster, 2+ petaflops, very, very high bandwidth and low latency network. And very, very good for existing MPI codes and existing hybrid codes. And then it has, each node has its at least one card in it, so you can always use the Xeon Phi. If you do native execution, so you have a code, you don't want to do anything, you just want to compile it so that you can run it on the Xeon Phi. you basically have to change only one compiler flag. When you compile for the host, you should have the compiler flag -x host. And if you want to compile the same code to run entirely or in its entirety on the Xeon Phi, you replace -x host with -m and then you get an executable that executes on the mic. And if you have built such an executable, you can be on the host. You punch into the prompt /a.out, something that you have compiled with -m mic, and the tool that launches your a.out code or executable will automatically figure out, oh, it has been compiled for the Xeon Phi, and it will automatically push the executable onto the Xeon Phi and run it there. So for native execution, you only replace -x host with -m mic, and now you get an executable for the mic. And at this point, I always like to point out, if you're running on Stampede and you compile for the host and you don't have X host in there, you should always add it. Without -x host, you will create code that is not, that doesn't contain any AVX instructions, but only the older instructions for the narrower vector unit. So without -x host on Stampede, you may leave quite a lot of performance on the table. But that's just a side note. So replace X host with -m mic, and you get you run on the mic. The mic has 61 cores. It's a little bit. It would be too much detail to go really into this. There are some programming models where you have to leave one core idle, and other programming models where you can use all the cores. So my recommendation to beginners is always think of 60 cores and multiples of 60 and leave one core idle regardless of what you are doing. And then later on, when you understand a little bit more what this last core does and when it is used and when it is not used by the runtime, then you can think about using 61 cores. And leaving one core idle on a machine that has 61 cores, that's 1.5%, so you don't have to worry about that. Okay, then the other programming model is a symmetric MPI. And we call that symmetric because you have MPI tasks on the host, you have MPI tasks on the mic. What is not symmetric is, of course, the performance characteristics. Those are completely different on the host and on the mic. But it is symmetric in a logical sense when you reason about your MPI. You can send a message from the host to the mic that is in the same box. You can send a message from the host to a mic in a different box or between two mics. In MPI, it doesn't make any difference. That's all done by the library. So wherever your MPI tasks are, you can just have a simple MPI send, a simple MPI receive. And it doesn't matter from the logical, from the design point of view in your code where these tasks are running, host or mic. So you don't have to change anything in your code to send messages from host to mic or mic to mic. So you're running exactly, or in first approximation, you're running exactly the same code on the host and on the mic. All the communication between host and mics are done through MPI. And so from an MPI point of view, everything looks symmetric. Everything is just one communicator in MPI, and there's no difference made due to the hardware. Which also means that there's high code reuse because you're running the same code on the host and on the mic. And the only thing you have to worry about is that, for the reasons that I discussed earlier, you need threads when you code for the Xeon Phi. So if you have a pure MPI code, you have to first add threads, most likely OpenMP, or if you do Silk++, or thread building blocks or pthreads, something like that. Okay, it is symmetric from the point of view, from the MPI point of view, but not when it comes to execution speed. So now you have to think about balancing your workload. And of course, like always in MPI, you have to think about locality. It is certainly faster to transfer or to send messages between a mic and a host that are in the same box compared to a mic and a host that is on the other side of the network. So you want to think a little bit about locality, and so that most of your messages don't have to travel that far. Yeah, so on the host, you typically use 1 to 2 gigabytes per task. You have 16 cores, 32 gigabytes of memory. If you apply the same rule to the Xeon Phi, which has 8 gigabytes of memory, then kind of a rule of thumb is that you have 1 or up to 10 MPI tasks per Phi on Stampede. If you go to a really high number, then you start congesting the PCI Express bus when hundreds of MPI tasks try to communicate through the PCI Express bus. And then depending on the number of MPI tasks that you have, now you assign a number of threads to each MPI task so that you can use the whole device, and that in total you're running 60, 120, 180, or 240 threads on the Xeon Phi. And the third model is MPI with offload to the Phi. So if you have code that you have already adapted to GPUs, then you're in a good situation. You have already identified the regions where you spend most of the time, and rather than having a kernel that is launched on a GPU, now you take this code and you launch it on the Xeon Phi. So porting your CUDA code back to something OpenMP shouldn't be, or should be pretty straightforward. If you haven't done that yet, then the first step would be to add threads to your code, identify the hotspots, add OpenMP to the hotspots, and then you can move on and offload those hotspots, those OpenMP parallel regions, to the Xeon Phi. And as I said, if you use MKL routines, you can do also automatic offloading. Oops, for that. So the good things about the Xeon Phi are that it is x86, a technology that we are all familiar with. You can stick to your familiar languages. You don't have to learn another language like CUDA or OpenCL. You can use your parallel programming models that you're used to. MPI is always there. That is basically the backbone of any cluster, any code that runs on a cluster. But for your threads, you can use OpenMP, which is the most widely used thread-based programming model. And then the good thing is you optimize for the Phi, and then you also gain speed on the host. So will my code run on the Xeon Phi? The answer is yes. But we always think that that is the wrong question, because what you're really asking is, will my code run well on the Xeon Phi? And what kind of performance will you get? And the answer is that without additional work, you will not get good performance. There are very few codes that are really so well optimized on the host that you can just take them and run them on the Phi and do very little tweaks, and then you get good performance. So for most of your codes, you will find out all the deficiencies in your code, and then you have to resolve them to get the good performance. And the other, I want to put a qualifier to the yes, will my code run on the Xeon Phi? Of course, if you're using libraries, and some of them are very, very big and complicated to build, then they all have to be built for the Xeon Phi, and that is something that also turns out to be a little bit of a bottleneck. But in principle, all your code should run easily on the Phi. So the experiences that we made is code ports really easily. It's just a recompile, plus you have to satisfy all the dependencies. You may have to recompile a lot of libraries. But performance, to get good performance, that here it says very optimistically can require real work. I can assure you it will certainly require real work. Getting the code to run, because it's just a recompile where you change X host to dash m might is almost too easy. And then the real effort goes into step 2, into the optimization. But scalability on the card, and that was a concern at the beginning, if you have 60 cores, 120 threads, and to have cache coherency, could be the scalability a bottleneck. But it's not really, that's not really the main bottleneck on the Xeon Phi. So scalability is pretty good. And then also getting your code to vectorize is really, really very important. You have these wide vector units. If your code doesn't vectorize, you leave close to 90% of your performance on the table. And I have 2 slides at the end where you can see 2 examples from our colleague Carlos. So he's doing a scaling study here on the host. That's a red line up to 16 cores. And 2 blue lines, the upper line is from some older test hardware that we have, and this line is from the hardware that we have actually in Stampede. And you can see at a certain number of threads, the performance on the mic is actually substantially better than the performance on the host with 16 threads. And here, in your code, you would experiment what number of threads gives you the best performance. So there's no real guideline there. So you just experiment. And the other example is a PETSI mumps example, where you see the scaling or the execution time versus the number of threads. And here you can see that Carlos tried 60, 90, 120, 180, and 240 threads. And here you can see that this code runs the best with two threads per core. So again, just to illustrate that for the number of threads, you experiment and find out what the best number is. And yeah, in other training sessions, we have a lab, and this is just the intro to the lab. Okay, that's it. Thank you very much. Yeah, do you have questions? We have 5 minutes probably, or till the next guy is ready.
This is a rapid for Intel. I mean, not rapid. I mean something that you know that is in this last slide. You can see combined with OpenQ or something.
Yeah, it's a PETSI version that has also threads, and we compiled it on the Xeon Phi, and then we ran this mouse example.
You mentioned that putting X house, how do you think this X house concept is combined for performance of code? I mean, what does X house mean?
Xhost tells the compiler to create an executable that uses all the bells and whistles that this hardware for which your compiler has. If you don't use Xhost, it creates an executable that can run on a large variety of hardware. And so it strips out all the AVX and goes to the previous generation, the SSE instruction, so that it can run also on pre-sandwich hardware. Okay. Who's next? Let's break.
Carlos is next.
Okay, Carlos is next. Okay, thank you very much.
That's fine. Just go to the view screen.
I don't want to open this, but I want to open the PPT.
Oh, if you want. I don't know. This one might be on this.
Yeah, I'm good. I tested before. Oh. Okay. Depends. Possibly. No, I'm just trying to. Do I have to open it within the
No, I think
within the guy? Because
no, that's just sharing the desktop.
that didn't work.
Here.
That just showed the presentation mode for everybody.
Oh,
And,
did it?
Yeah.
Okay, yeah, I know how to fix that. It's swap displays.
Oh, cool. Coolness. Thank you, sir.
No problem.
All right. Since my colleagues only went 20 minutes late, I'll try to make this short and sweet. So my name is Carlos Rosales. I work here in the HPC group. Been here for about 5.5 years. What I'm going to try to cover today, if this works. If it doesn't do it that way, we can do it that way. Okay. So I'm going to talk to you very briefly because somebody has talked to you a couple of times about this already, models of parallelism. And I'm going to talk very, very quickly about system architectures. Then we're going to cover what we can cover about hybrid computing in about an hour. And then I'm going to talk about task and thread affinity because these are going to be critical concepts for running hybrid codes. There's only a couple of key ideas that I want to get across in this class because I could really be talking for a couple of days about hybrid computing. So I will try to make sure that you guys get those two. And if you think I'm going too fast or too slow, just stop me anytime during the talk. So I'm pretty sure you've seen something similar to this during the two-day course already. We have two typical programming modes. One of them is, oh, this guy's completely dead. That's sweet. One of them is OpenMP, or this system just sucks. Okay, so apparently I need to stay still and move here and be a good boy. Okay, so we have a shared memory model that we normally program with OpenMP, but this could be pthreads, it could be TBB, it could be whatever threading model you want to use. Essentially a fine-grained model of parallelism that where every single core or processing element has access to the memory. And typically what you have is a single executable, a single a.out that spawns all these threads, and each of them access the memory. Then you have the distributed parallelism model, which is mostly used with MPI, the message passing interface, where each core has its own private section of memory. It can access that memory only, and when it needs to communicate with other tasks, it needs to send an explicit message saying, hey, I wanted to receive this amount of data. Both of these have issues when you start going to a certain scale or to a certain complexity on your physical model that you're trying to represent in the computer. Essentially, if you're just doing OpenMP, you get severely limited by the amount of available memory. You have some large shared memory systems, but these are terrifically expensive. So you will see very few of them deployed within XSEDE. And the reason is that the cost per node of those is just exorbitant. There are other issues with having very large OpenMP systems, shared memory systems. One of them is related to thread affinity that I will cover later on. Essentially, what you have to think is that when you have a shared memory system, it might appear as a completely flat memory system to you as the programmer. But in hardware, this is not possible to do. You will have several layers. When a executing core is on this corner of the computer and the memory needs to access is on the other side of the computer, there will be several layers of indirection that has to go through And so it can access that data, but the speed of access is not going to be the same as accessing completely local memory. So that can lead to codes that work in shared memory, but they're not very efficient. The other limitation is a very hard limitation on the size of your problem. You cannot run a code that is very, very complex in the amount of physics that it brings to the table. And I'm using physics because that's my background, but whatever you're doing, I think you understand my meaning. You cannot increase your complexity too much because at some point you just run out of memory. And if you cannot communicate with somebody that is outside your box, your little box or big box, whatever it is, then there's no way for you to expand any further. There are other limitations, but these are mostly of practical nature when you're developing code. And these are that even though very often people say, hey, you want to parallelize something, use OpenMP first, it's really easy. Well, the truth is that there are many, many subtle bugs that you can introduce in a shared memory code, which are very difficult to catch because the code may still work. It will actually work in most cases, but at some point you're going to realize that there's a problem. And finding those hidden issues, those racing conditions, can be a little bit tricky. So, and I think the reason for this is that we humans tend to think on terms of serial access. We don't tend to think of, oh, you know, I'm going to do 75 things at the same time. We tend to think about, oh, I'm going to do this thing, then I'm going to do this thing, I'm going to do this thing. And that's more similar to an MPI or distributed memory paradigm. Yes? Oh, that depends. I mean, it can go from gigabytes to terabytes. I mean, you can have very, very large SGI systems in particular, make very large shared memory platforms. So you can have a very large memory footprint. The reason we as a center don't deploy very large shared memory systems, apart from the large memory nodes that we have that have 1 terabyte of memory for 32 cores, is just because of the expense. We believe we can provide a much better service to the community by providing much larger systems and then providing some of these large memory nodes, which are smaller in number, to help people that cannot scale farther than a node.
Large queue is with NUMA.
Actually, every single node, and I'm going to show you some slides now when I'm talking about architecture, is going to have some level of NUMA. Unless you have, well, let me get into that in 2 minutes. So that's for shared memory, and I say OpenMP, but please, throughout all these slides, when I say OpenMP, just think threads of any kind. MPI has its own limitations too. If you have multi-core CPUs, and we now do on almost every system out there, and you're going to run many nodes or many cores, you will have lots and lots of MPI tasks. Those are relatively heavy in terms of resource needed by the MPI task compared to OpenMP. So the runtime, the MPI runtime starts first taking a lot of memory on its own that you cannot use for your own simulation. It also starts having trouble just handling all these threads. For example, it comes to the point that if you want to start a 50,000, 100,000 core job, you might have to wait for just MPI init to connect to everybody for 30, 40 minutes just to get started without your job even having done anything at all. So running at very large scales only with MPI starts to be a problem. Another issue that we don't normally discuss very much, but it's important for you to know, is that the actual bandwidth that you get out of your MPI network communication of InfiniBand or any other interconnect that you have is not completely homogeneous. I like to use this picture. It just shows the type of bandwidth you can obtain if you communicate from one task in one node to another task in a remote node. You'll see if your message size is really large, it's about a megabyte or more, you get the advertised performance, which is over 6 gigabytes per second. Now, if your message size is really small, it's in the a kilobyte or something like that, which is not uncommon. I mean, there's plenty of codes with average message sizes on the 10 kilobyte range. Many computational chemistry codes are in that range. Then the bandwidth you get is significantly lower. In this case, around 1 gigabyte per second, right? So if you have many, many tasks, and each of them is working on a fairly small volume, your message sizes are going to be small. Your efficiency in the exchange of messages is going to drop down in this figure. And overall, you're not going to see a very good performance, even though you're doing everything correctly in the code. When you use OpenMP or other threading model, you have less tasks and a larger volume per task. So each of your messages is going to be larger. And so you're exchanging the same amount of data, essentially, but you're exchanging it at a much faster rate. And that's because messages that are really small, the communication is dominated just by the overhead of setting up all the MPI exchanges. Whereas messages that are very large, that setup time is really in the noise compared to the amount of time that it takes to move your bytes through the actual physical wire. So both systems on their own have severe limitations. And I'm going to get down to system architectures that you were mentioning. So when we think about programming models and then we think about hardware architectures, typically we have SMP, symmetric processing systems, single memory space accessed by all the CPUs, not necessarily in the same time. So this CPU, if it has to access memory that is up here, is going to take longer than this guy accessing memory that is up there. But overall, relatively easy to understand and map to an OpenMP or a threaded processing paradigm. On the other hand, we have clusters where, in the old times, we had single CPU, single core, accessing some local memory, connected to a network interface card or a host channel adapter, we call them now. All these going to a network switch of some type and just exchanging messages. Also, easy to map to MPI. There's only one guy here to access memory. There's not really any need for threading. You cannot get out of a single node that is represented by the gray little box there using threads anyway, because they cannot communicate through the network. So you're going to have to use MPI if you want to use more than one. All fairly simple, all really not applicable to any system that you run on today. Well, so that may be large SMP systems, but they're pretty rare. What we have today is something more similar to this figure, where each node has at least 2 sockets, sometimes 4. They're connected to each other so that they can access remote memory. One of them is typically connected to the network card, so not both of them, so you have a small asymmetry there. And on top of these, you can have, well, the network here is also more complicated. You will have, inside the rack, we have several nodes. Those will be connected to a lift switch on the rack that goes to a core switch that connects multiple racks. And several core switches are connected together to provide connectivity throughout the whole system. So the network is more complicated. Your nodes are significantly more complicated. And this picture doesn't even show accelerators. So this picture doesn't show a mic. This picture doesn't show a GPU. This picture doesn't show an FPGA. So you could have additional levels of complexity here. The point of this picture is to try to give you an idea of why you might want to use a hybrid model. Because you can see from this that just by running a shared model inside the node and 1 or 2 MPI tasks to communicate through the network, you might be able to do something that is more efficient. And even though these are all good reasons to use hybrid, hybrid is not always the answer. Very often, if you're running on a scale that is not very large, say 128 cores, 256 cores, you probably have no need to use a hybrid model. In that case, MPI is probably good enough to give you fairly good performance, because modern MPI libraries have already sections in them that allow them to be very efficient when they're working on node. So their message exchanges when they're on a single node will go through shared memory. They will be roughly at the same rate that if you were just doing a memory access. So they're extremely fast on node. And unless you have tons and tons of tasks, you may get away with just a pure MPI code. But still, if you want to get larger than that, using hybrid is a very good idea. It's essentially the only way you're going to be able to get to significantly larger core counts. Or if you want to run on an accelerator, you want to run on a GPU, you need to understand what a thread is. you need to run on a mic, you need to understand what a thread is. If you want to run on multiple GPUs, multiple mics, you're going to have to use both models. So it's important that you understand some of the concepts, even if you're not going to scale very large, but if you want to use an accelerator of some kind, some of these things might be useful to you. Now, the way that we normally go about hybrid programming, and I'm not going to teach you how to do an amazing hybrid code today, because it's just not possible in half an hour. But the way we normally would go about this is you already have a sequential code that is working, but you want it to be faster. So the way I would probably go about this is I would parallelize it with MPI first, because that way I can go across nodes, I can get a much larger memory footprint, I can run bigger cases that are more interesting to me. Once I have that, I would add OpenMP, because I already have a communication pattern that works and is efficient, and I just need to essentially parallelize probably my inner loops, well, not the innermost loops, but my heavier loops with OpenMP. If you already have an OpenMP code, then it's different. Then the approach I would take is say, okay, let's assume this is a sequential code. And now I'm just going to put MPI communications between different tasks using only the master thread. So you have MPI and OpenMP, but they don't talk to each other at all. When you do MPI exchanges, they appear to be as if you had a serial code. And that's the least error-prone way to do this. So when you mix MPI and OpenMP or other threads, you can do all sorts of crazy stuff. I mean, you can be communicating from all threads to all threads using tags to identify threads, and I will give you an example later of how to do that for a simple case. But that's typically not very safe, because it makes your code difficult to maintain. You might have a very good reason to do it, and then that's fine, but that shouldn't be the first thing that you think of. The first thing that you think of should be, okay, I'm going to distribute my code using MPI, then I'm going to parallelize several sections using OpenMP, but these two things are not going to know anything about each other. So all the MPI exchanges are going to come from a single thread rather than from multiple threads. That last statement there, I don't think I included the example. Essentially, overlapping computation and communication is a great idea, but typically you're going to do that with the MPI part. Essentially, the OpenMP part is not going to be involved. If it is, then things become very tricky, and I don't think we want to spend time on that today. So this is a trivial example, and I've tried to put all examples both in reasonably understandable C and Fortran. This is a trivial example of a hybrid code that really doesn't do anything. What you have is you initialize your MPI with the three typical calls: MPI init, MPI comsize, MPI comrank. Then you will have some loop that you feel needs to be accelerated. In this case, we're just going to use a simple pragma OMP parallel 4 or OMP parallel do. And after you're done with everything, you will call MPI finalize, and you're done. So, trivial example. As you can see, it's not very scary. Anybody can do something like this. Now, you'll notice that I've used MPI init here. So the MPI library knows nothing about the fact that you're threading parts of the code. At this point, the MPI library is going to apply any optimizations that it can on the runtime and any optimizations that it can during the build of the binary, ignoring the fact that you might have threads in here. And I have to say, that's the way I write most of my code. But you can use an alternative way to initialize MPI that gives the MPI library and runtime hints regarding how you're going to write this code and the fact that it's thread. So you can use MPI init thread with several options. You can have a thread single, which essentially means, hey, only one thread is going to execute throughout the code. You can use MPI thread funneled, which means only the master thread is going to execute MPI calls. So you can make optimizations that assume that only the master thread is going to do MPI calls. You can use thread serialized, which means any thread can make calls, but they're only going to happen one thread at a time. So I'm not going to have two threads simultaneously making MPI calls. And MPI thread multiple, which is just going to be a crazy code. I'm going to send messages from everywhere, and we'll see what happens. Question? So both. The runtime can decide how to switch algorithms for certain MPI calls, depending on what's happening during runtime, depending on the message size, depending on who is making the call, and so on and so forth. So the answer is really both. And it varies a lot depending on which MPI library you're using. Now, if you're going to do calls just through the master thread, which would be my recommendation, you can use the MPI thread funnel. All this is saying is, look, every time I'm going to make an MPI call, I'm only going to make it from the master thread. All the other threads don't exist. So what it's telling MPI is, I'm going to have some OpenMP sections in my code. All the MPI calls are going to be made outside those parallel regions. And outside those parallel regions, if you remember how OpenMP works, OpenMP essentially starts with a master thread. When it hits a parallel region, forks a series of threads. When it finishes the parallel region, collapses them, continues with a single thread. So it's only from that single master thread that I'm going to make MPI calls. And for performance purposes, what typically happens is when a parallel region collapses, the threads are not killed. They're still there, they're just spinning idle, and they're not participating on any of the execution. But they're not killed because otherwise, if you open a new parallel region, there would be an overhead related to starting up, spawning those threads again. So at a practical level, the threads are there, they're just not doing anything. But that's not something that affects you as a person writing the code. An example about using MPI thread funnel, and I know this section is kind of dry, but I just want to give you at least one example of each of the use modes so that if you ever want to use them, you have something to refer to later. When you use MPI thread funnel, what you want to do is you want to make sure that you have an MPI, you have an OpenMP barrier before you start your MPI exchange. So before you have your MP master region, you want to have an OpenMP barrier. The reason for that is that typically each thread will be contributing something to the array that you're going to exchange using MPI. So you want to make sure that all OpenMP threads have finished writing their data to memory before you pack that array and then you send it. The same, an OpenMP master section does not have an implied barrier at the end. So all an OpenMP master section means is when you get here, only the master thread is going to execute the contents, but all the other threads can continue. So you want to put an OpenMP barrier here so that if you want to access the MPI buffer that you just exchanged between two processes, all the threads access the new stuff. Because you could imagine a case where I pack some buffer, I send it using the master thread to my neighbor. If I don't have an OpenMP barrier after that section, as soon as thread number 2 is through that section, and thread number 2 is through that section immediately because it doesn't participate on the MPI exchange, it can try to access the array. And that array might not have arrived yet to the network because MPI is still processing it. Or the master thread is slightly slower and it has delayed on sending the message. So what you want to do is you want to make sure, okay, master is doing this. While master is doing this, any thread that falls through is just going to stop at the OpenMP barrier and wait for the master thread to reach this barrier and say, hey, I'm done sending my MPI stuff. Question?
So if I use funnel and
Sorry, if you use?
if I use a thread funnel, but I nevertheless, because of a mistake, try to do computation from the other threads, does it go through and you just have blocks that you want, you know, or
So most likely well, depends on the compiler. Depending on the compiler, it might go through, and then you will have bugs that are fairly difficult to find. Or your compiler might be good enough to say, no, you told me it was going to be funneled, and you're making a call within a parallel region. So I think most compilers would just let it through, and you would actually have a pretty strange error at some point.
runtime?
Runtime typically doesn't check for this. It checks for other things if you ask it to, but not for this. You can also do MPI calls from a single region, and in a single region is not the master thread that executes the call, but whichever thread gets there first will do that call. And that can be useful sometimes to improve your performance. The thing to remember here is that a single region has an implied barrier at the end, so you don't have to use the barrier that we just showed for the previous case. So a single region has an implied barrier here in the OMP single, or when you reach this bracket that closes the OMP single region, you will have an implied barrier. So there's no need for you to worry about synchronization at that point. Then you could make calls from all threads, which would be using this MPI thread multiple. I always advise against it because it's fairly difficult to manage. I mean, you get yourself into a lot of trouble. In most cases, you don't need to. In most cases, you don't need the ability to, send from task 0 to task 1, but actually use thread 7 to talk to thread 15. Typically, that's not needed. Typically, you can redesign the way that your code works to avoid that kind of complication. It makes the code really difficult to maintain and to debug, especially if you give it to somebody else that hasn't written it. It makes things pretty hard. What you can do is write a code like this, and I hope that if you're a C programmer, you will follow this. Essentially, your $OMP will be pragma OMP, and the rest is actually very, very similar. Just that you don't call keyword. So this is some function that we have defined, right, to do some parallel work. And when we're done with that, we're going to do an exchange between processors 0 and 1. And this example would only work for 2 processors because you will notice that there is an if-else. So if you have more than 2, you need to modify this. But essentially, task number 0, MPI task number 0 is going to do an MPI send. It's going to use MPI task number 1 as the destination for the message. So I'm sending to task number 1. And it's going to use its own thread ID as the tag. So it's going to say, hey, I want to send something to MPI task number 1, and I'm going to use this message tag to make sure that it gets to the right place. Because if you didn't use a tag there, or you put always the same tag for all the messages, the MPI runtime will have no way to match messages from different threads. It would have 7 messages in the queue going to rank 1, to 7 different threads, but it doesn't know which ones. And most likely, the runtime would actually match them. It will match them first come, first serve. If there's a receive also that says, hey, I'm task number 1, and I'm waiting for a message from task number 0, it will just match those 2 and get moving. And you will get some really strange errors at some point. Or not errors, but results that are invalid, which is even worse, because that's a much harder thing to debug. On the other hand, the task doing the receive is saying, I'm expecting to receive something for source MPI task 0, and I'm expecting that it's going to arrive with this thread ID. And that way you can play with the source destination and the thread ID as the MPI tag to exchange multiple messages. Now, if you can avoid this, by all means, avoid it, because it can get pretty nasty very quickly. This is one thing that is very difficult to debug. Even with the parallel debuggers that I think Robert is going to talk about this afternoon, this creates problems that are very easy to catch. So that's all I wanted to say about hybrid computing, how to write hybrid code, because if we get any farther than that, we'll be talking here for a very long time. Do you have any questions about what I just said? Okay, so it's either crystal clear or so muddy that we don't have any questions. That's okay. The main thing that I wanted to convey with that section is that if you need to go to a certain scale of computing, you should probably think about hybrid. With the number of cores that we have, on each node right now, it's going to be worth spending some time learning at very least threading. But if you can keep MPI and OpenP separate, that's going to make your life much easier in terms of debugging your code and producing code that is sustainable. Now, in the next section, I want to talk about hybrid applications and some of the issues that you have at a practical level when you're executing hybrid applications. Because you might not be a code developer, but maybe you're working with an application that has both threads and MPI, and you need to know how to run it efficiently in a system like this. Right? Now, well, you can read the definition, something that has MPI and some sort of threading, that's fine. Now, something important is that hybrid execution is by no means guarantees optimal performance. And I made reference to this before when I said if you're running at a smaller scale sometimes, you're just better off with a pure MPI code. Now, for scaling purposes, or if you want to run on a mic, for example, you're going to have some threading. Because the mic is not designed for running MPI. A GPU is also not designed to run MPI. So some threading is going to be required. The key here is to think about NUMA. And so NUMA stands for non-uniform memory access. That means it's something I mentioned before. You might have a lot of memory which is accessible to all the processing elements, but the accessing time is not homogeneous. So the problem with NUMA is that you, as a user, you need to control where a thread is going to read its memory from, where a thread is going to be executed on. Because if you don't do anything, the operating system will typically float threads and it'll say, oh, you're running 16 threads, that's fine, but core number 15 is not really doing very much right now, and core number 3 is really busy, so I'm going to swap those two threads. Now you have a context switch. Now this thread arrives to a core that has locally none of the memory elements it needs. So now it needs to access memory remotely from the core that it was allocated before. It will keep doing this until your performance essentially drops by about 50%. And that's a common case when you don't pin anything. There is a case that is even worse. Say that I have the example on the right. I have one MPI task and 16 threads per task. Now that figure is assuming an optimal situation where I have a master task, it spawns 16 threads, and each thread lands on a processing core. That doesn't have to be the case. For example, if you use MVAPIC2, the MVAPIC2 library, and you don't unset affinity or set affinity very carefully, by default, the MPI task will not be allowed to move from core number 0. By default, all threads spawned by that task will be spawning core number 0. So you will have 16 threads running on a single core and 15 cores idle. So that's a horrible setup because your code now is not going to be 50% slower. Now your code is going to be more than 16 times slower because each thread execution is going to be serialized. It's going to run thread 0 for a few milliseconds, then thread 1 for a few milliseconds, then thread 7, then thread 2, then thread 15. It's going to be terrible. So you have to be very careful the way your MPI task set, your MPI task affinity is done and your thread affinity is done. What this shows is a little bit the variability in the options that you have when you have a hybrid code. You can essentially run your hybrid code as if it was a pure MPI code with a single thread per MPI task and 16 tasks. You can do something that many people do because this tends to be quite efficient. Run one MPI task per socket and then as many threads as cores you have on that socket. The reason that's efficient is that you combine the memory access so that it's local to the socket. And so you can have a fairly good memory bandwidth performance with that type of setup. And then if you're looking for ultimate scalability in terms of MPI, using a single task per node is also something we see very commonly amongst codes that run very large simulations on our system, just to avoid having issues particularly with collective exchanges, because collective exchanges scale very badly with the number of tasks involved, particularly non-rooted exchange like all-to-all, all-to-all V, and so on. So this is just the variety of settings that you can do. Now, what is important is that you need to be able to do this NUMA control. So from now on, I'm going to focus just on the affinity for the threads and how to set them up. And I'll talk a little bit more about how to set the MPI task affinity later. I showed you before that we have these multi-core systems. They're not completely symmetric because they're connected to different things. So one socket might be connected to the network card, while another socket might be connected to disk, and so on. Well, that's if you're using local disk, if you're not using the share file system. If you had a single core that is slower than the others for some reason, is handling all the OS interrupts, is doing something else, you might want to avoid putting too much work on that particular core. And using NUMA control allows you to do that. So there's a command called NUMA control. Well, okay, I went 2 slides too fast. So using NUMA control, you can specify both process affinity and memory affinity. So you can say, this thread, or this MPA task, is going to execute on this core and this core only. So operating system, don't touch my process. Right? It's running here, I don't want it to swap, because I want to know what's going on. You can also specify affinity for the memory settings. You can say, I want memory access to be local only. That is, okay, this task can access only memory that the OS has assigned to this socket. And if it goes over the memory that the system has assigned to this socket, just crash. Tell me that you don't have enough memory. You can say preferred affinity, memory affinity set to local. So try to do as much local access as you can, but if you need more memory, go ahead and go to a remote memory location. And when I say remote in this context, I'm talking remote still within a single node, still within shared memory. It's just remote to that socket. So these two are very important. And there are some kernel defaults that are typically the way that the system controls NUMA, but as a user, you can change them. And you can change them in several ways. You can change them by getting a process ID and using that process ID that is already running in the system and change its affinity. Now that's very clunky, especially when you have lots of process IDs. You don't want to do that. You can change it within the code using an explicit API that controls affinity settings, typically with get SCED affinity or set SCED affinity, and you provide a mask that says, okay, these are the places where I want you to place tasks. These are the places that I want you to allocate memory. Or you can do it at process execution. So you have a wrapper that says, hey, I'm going to run this code. I want to apply these general settings for my affinity. And that's actually what we normally do here at TACC. I'm going to go over a few minutes. I know it's almost 10:30. We have a lab that should only take really 30 minutes out of the hour we have it scheduled for. So what I'm going to do is I'm going to go probably 5-10 minutes over. Now we have the break. We have our 15-20 minutes of break, and then we come back for the lab. Is that okay? So NUMA control is the command that actually handles how to set these things from the command line. And it's actually a very, very easy command to use. It allows, well, let me go over one thing that I haven't mentioned. And I should have had a slide, but I completely forgot. So you see these two sockets that represent the Stampede sock compute node sockets. Each of them has 8 cores. And there's some numbering scheme up here, 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. Now, this numbering scheme is not fixed. This numbering scheme depends on your BIOS revision, depends on a whole bunch of things. So in Stampede, in the compute nodes, we have this numbering scheme, where this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So it's a completely contiguous numbering scheme. Now, in other systems, you might have 0, 1, 2, 3. You might have an alternating scheme between the two sockets. And it's important that you know that when you're going to set affinity, especially if you're not binding to the socket, but to a specific core. There are several tools that allow you to do that. I mean, you can ask the people running the system, and they should be able to tell you. But if you want to do it on your own, there's something called HWLock, HWLOC. There's a library that you can install, very easy to build, and you can execute on a compute node, and it will essentially produce either text output or some fairly nice figures that have all the cores and their actual core IDs, so that when you do your affinity, you don't make a mistake and you don't bind to the wrong thing. So let me go over some of the options that NUMA control has. And the way the NUMA control is going to be used is just going to be NUMA control, whatever options to specify the way affinity has to be set, and then you're executable. So it's pretty simple in principle. Now, there's lots of options for NUMA control. If you just want to set socket affinity, then you can use -n or -CPU node bind, and you will say socket 0 or socket 1. And you can do that by MPI task. So you could say, okay, I want task number 0 to go socket 0, task number 1 go socket number 1. And you can script all these things. So memory policy, you see there are several options there. Local allocation tends to work really well for most cases, unless you have very, very large share objects or very, very large share arrays where multiple threads are accessing from both sockets. In that case, probably using an interleaved setting works better, because that way, if you have to access something that is far away, it's not always that you have to access something that is far away, but on average, you're going to be averaging down the worst case scenario, essentially. You're not going to get the best performance, but you're going to get better than what you would normally get with just local access. And getting the best performance would really require you to know exactly where each piece of the array is going to be landing and do a dynamic change. And that might actually have more overhead than just doing an interleave. Yeah, and I think you can just read the rest. The only one that is probably also important is the ability to set core affinity directly, so that you can say, I only have 2 tasks. I want to set them out on 0 and 8 to make sure that they're running on separate sockets. Now, the way you set this is typically, we have some recommendations for best practices. And typically what you want is your MPI tasks to be evenly distributed across sockets. So you have 2 tasks, 1 in each socket. If you have 4, task 0 and 1 on the first socket, and 2 and 3 on the second socket. Try to have the same number of threads per task. There are some cases where this does not apply. You might have a code where one particular task does a lot of I/O, and it's very, very I/O intensive. In some of those cases, you will have to do a slightly different distribution, but they're very specialized. So for those, you need to investigate it in detail, or if you see some behavior that you don't think is correct, you probably want to contact us through the help desk, and then one of us can work with you to find out if there's a better way to do things. But in most cases, this is one even distribution. Memory policy for MPI is always, local is always the best. Now if you're running just threaded, like I said before, in most cases local works best, but if you have very large shared arrays, interleave might give you a better bandwidth throughout the execution. Remember that once allocation happens and memory is committed, the location where that memory resides is not going to move. The thread might move, but your memory is not going to change. I've mentioned this before in different contexts, but just to remind you, when you're running hybrid code, if you set a number of threads in the environment with OMP-num threads, for example, each MPI task that executes is going to spawn those threads, and those threads are going to inherit whatever affinity the MPI task that spawned them had set to it. Well, I guess technically the MPI task spawns the master thread spawns the threads, and they all inherit from their parent. but to more practical things. So how would you set up a batch script in a Stampede to send something that is hybrid? This is an example where you're going to use 6 nodes, and each of them are going to use 16 OMP threads. So it says there, make sure one MPI task is created on each node. This is just for the example. You might want to create 2, 1 per socket, like I mentioned before, and then your OMP num threads will have to go down to 8 to make sure you're not overloading cores with multiple threads. Right? So the product of your number of tasks and number of OMP threads should ideally always be equal to 16, so that you're using all the cores but no more. So in the example you see, we have this. If you're familiar with the, I hope you're familiar a little bit with the Slurm system we have at TACC. Essentially, you have 2 variables inside the script that control how many nodes and how many tasks you get assigned. Capital N is the number of nodes. In this case, we asked for 6. And small n is the total number of tasks. So we asked for 6. That means we have 1 task per node only. We export OMP num threads to whatever we need, in this case 16. And then, if you're using Mbappage 2, you will need to do this because you want to make sure that the default setting, which is, hey, let's run everybody on a single core because this is so clever, doesn't take place. Okay, that's something that Mbappage actually have somebody that used to work for the Mbappage 2 development team, and we have a good relationship with them. And we keep telling them, you know, you cannot have these as default settings because people get surprised. They go, my code is 20 times slower than it used to. Why? It's like, well, the default affinity settings that Mbappage 2 has are really terrible. So you can use these environments, these 4 environmental variables. Actually, these 2 are not needed in Stampede anymore. This is for Mbappage 1, not for Mbappage 2. The top 2 are for Mbappage 2. All they're going to do is let the MPI tasks float everywhere. So the operating system can move them around. So by doing this, what you're saying is this MPI task can run anywhere. So when I execute my OpenMP thread, they can also run everywhere, which typically means they're going to land on separate cores until all cores are busy. Now, you're going to do your IV run, NUMA control, minus I, all A dot out, and if we go back to the table that I showed you, you will see that the minus I indicates that I want an interleave memory policy, because overall that will give you the better memory bandwidth, and all means use all sockets available. So this will give you something that runs okay. It's not fantastic, but it's going to give you a reasonable setup. If you were using, like I said before, a different number of tasks, things are a little different, but not very much. Essentially, you will have, again, the same number of nodes, say 6, but now we say small n equals 12, so we have actually 2 MPI tasks per node. Thus, we reduce the OMP num threads to 8 to make sure we still have 16 per node. And what I'm doing here is I'm showing you a little bit a way to do this a little bit differently. So we have IV run and then numa.sh a.out, and inside that numa.sh script, we're going to bundle a bunch of different things. So we're going to unset the MPI affinities. We can automatically get the MPI rank that we want, and each of those PMI rank 0, PMI underscore ID, and so on. Each of those is for a different MPI stack. And don't worry about this. I'm going to show you how to do it without knowing that stuff, because this is painful. But essentially what this is going to tell you is this is what my rank is right now. I'm going to assign it to local rank, and then I'm going to go and I'm going to find out in which socket that rank is. And then I'm going to do a NUMA control, CPU bind, CPU node bind to that specific socket, mem bind to that specific socket, and execute. So overall, what this is going to do is going to bind your execution of each task to one socket and make sure the memory is bound locally to each socket for each task. And you probably don't want to be writing this every time you submit something. You probably don't even want to mess with all these variables. It's perfectly understandable. So what we have is we have a TACC affinity script that does this and a bunch of other things and sets up what we think is a very reasonable setting for hybrid execution in a Stampede. So the only thing you really have to do is you do IB-run, which is essentially our MPI launcher, TACC affinity, and your executable. Now, if you want to know what's under the covers, I will show you at the end in about 30 seconds. Some of the things we do in TACC affinity. But if you're running hybrid code, remember to use TACC affinity, especially if you're using the default Mbappage 2 library. Because otherwise, your performance is going to look really terrible, and you're going to be wondering, what did I do wrong with my code when your code is probably perfectly fine? It's all in the runtime selections that you have not made. Okay. So TACC affinity is critical if you're using hybrid code, unless you know what you're doing and you just set everything by hand. But this is the easiest way to get a very reasonable performance. And I'm going to go over TACC affinity very quickly, and then I'm going to show you the summary. So if you want to see what TACC affinity is just a script. What you can do is you can just type which TACC affinity, that will show you the full path. You can copy it to your account, and you can go over it and see what we actually do. The same with IB-run. If you want to know what IB-run does, you can just copy the script to your account and look at it. There's nothing secret there. There's nothing special. You know, it's just a bunch of scripts. And essentially what TACC affinity does is, like I mentioned before, it disables affinity for everything. And now it has a few more entries because we didn't used to have the Intel MPI stack, but now we do. So we also do a couple of things for MPI. It locates the rank as reported by the MPI runtime of that particular MPI library you're using. Then it detects, depending on your rank and on which system attack you are, because different systems have different core ID structures. Some of them are contiguous, some of them are round robin. Detects in which socket you're running, and then once it has detected in which socket you're running, it sets up the run to be evenly distributed between the two sockets. So it's just a fairly simple script. It's just that we decided as a user you shouldn't have to go through the pain of doing that if you don't have a particular need to test something very specific. So in summary, if you use hybrid computing, you get the ability to exploit the best parts of both shared memory, the shared memory programming model, and the MPI programming model. It can reduce your overall communication. It can also improve the efficiency of the communication that you do have. It can reduce your memory requirements per node, particularly a very large execution sizes, and particularly if you're using collective communications. And all these reduces your runtime overhead essentially, because the MPI runtime overhead is higher than what you get from just running threaded inside the node. Very important to control your affinity. If you're not controlling affinity in some way, either using TACC affinity or setting up your own affinity settings, you're going to find out that things work terribly badly. Something, I don't know if one of my colleagues has gone over this. If you're using mics and you just want to use one mic, there's an environmental variable to use for the Intel runtime, which is KMP_affinity. It has some very simple settings to distribute the threads amongst different cores in the mic. If you want to know more about that, you can ask me anytime. We can talk about that later. And then, as a user, you have control over where things are pinned, where the memory is pinned. You have control over everything. You just need to be conscious of the fact that now that you're running hybrid, it is very important where everything is actually executing, and take steps to make sure that everything is running in the right place. And yeah, that's pretty much all I had to say. Thanks very much. Do you have any questions? No? Then let's take a break, and say in 15 or 20 minutes we can get back to the lab. Thank you. Oh, go ahead.
Oh, you were in. That's fine. I was just gonna... Wow.
Ah, thought you had one set up.
No, no.
Okay.
That's good policy. Nice change. I like it. Before, we didn't move forward.
I mean, I can map it now. This is not. Hey, there is some heat. Use one control.
Yeah,
So the images are set in your code. It means that it's something we need. But if you want to do
Well, so I have a very simple lab that shouldn't really take anywhere close to an hour. Um, Essentially, what you're going to do in the lab, or the scripts are mostly going to do for you, and then I want you to look at the results and see if they match what we discussed in the class. Is first run NUMA control on the execution of a serial, of an MPI, and a hybrid code, and see how the different options for NUMA control are going to change the execution time that you see at the end. So if you should connect to a Stampede, just SSH to a Stampede, and then follow instructions here. You just need to extract that NUMA hybrid.tar directory. And, and I think if you all have the slides, then you can just follow them step by step. And I'm going to be around here, and we have 2 more people back there that are ready to answer questions as you go through. Like I said, mostly you're going to have to submit a couple of jobs. Now, you all should be on a reservation, so the job should start running almost immediately. And that's pretty much it. So just go for it, and if you have any issues, let us know. If you have any issues untarring the file, let me know. Like I said, this is a pretty simple lab because the JavaScript actually has all the settings for NUMA control. Just to begin, just SSH to Stampede with the account that you've been using. Once, yes? Oh, it should be on your. Okay. Just wait a minute. Just read it to me again. Any capitals? Okay, so sorry about that. In your submission scripts, there's a line that says $S batch dash A training blah blah blah. You're gonna have to change that to this guy. No. So let's go through this. 0, 3, 8, 11. So the first few are essentially doing local memory binding with -L, and then binding your execution to one specific core. Right? And you will see the first two are both within the first socket, socket 0. Second two are both within the second socket with 8 and 11. And there you could see differences in performance due to the fact that I need to think this because I think it's socket 1, so 8 through 11 are typically busier than socket 0. So which one gave you better performance?
The best overall was 0.
0.
It's better than letting them just with no localization.
Mm-hmm.
No localization is on the worst.
Yeah. And how much? By how much difference?
In the second best.
So 8 was 1.50.
1.5.
And then the next lowest was 1.55.
And how much did you get for 0?
Something similar. This
Okay.
is the second decimal place.
Mm-hmm.
1.50 versus 1.51.
So small differences. Small differences compared to, especially when you go to the very last two cases where you have -M1 and it's just bound to a socket, right? And it's actually bound to a socket, but let me slow down. So you just see small differences when you run between 0 and 3 and between 8 and 11. There can be small differences between 0 and 8 or 3 and 11 because they're in different sockets. But still, you're only doing one thing with one thread. So even though socket number 1, which is, of course, 8 through 15, is usually busier, you might not see a very big difference. You might see a small difference, but we would probably have to run these 10 or 20 times and take the average to see if there's any real difference. Right? So small differences are expected, but not very. Now, with the interleave option, what you're going to have is some of the accesses are going to be remote, so you might not get necessarily the same performance as before. Your runtimes will probably increase a little bit. Not a lot, but maybe 10, 15%, something like that order. Because most of the accesses are probably still local with some that go to the neighbor. In the last two cases, when we're we're essentially binding the memory to one socket, but we are executing on the other socket. So all the memory accesses are remote with respect to the socket. Those two should give you the worst execution times, and probably by a factor 20, 30% worse. Yeah. So this is essentially what this wants to illustrate. If you bind to a different core, but your memory access is still local, then the differences are small. When you're accessing memory remotely, because you're either interleaving or because you're forcing things to be placed remotely, then you get a much slower performance. When you don't do anything at all and everything is floating, you get something that is not very bad. It's very similar to doing a local binding because they always is going to try to keep things local. The only problem with that is that when you complicate things with MPI, then you can have issues because you can end up with all threads running on a single core. But this is what this first exercise is intended to illustrate. Essentially, the problems with accessing remote memory within a node. Now we have.
Let me make a comment.
Yes,
This
please.
is wrong. Like what I saw was in general was that I got what I consider marginal improvements by going in and trying to fiddle with it to localize it. But I have the potential to really damage it when I did it wrong.
Yes. So that's a very good point. So defaults typically work well. Now, that's not even that doesn't have any MPI, so you're not working with the task affinity. You're only working with the thread affinity. That's one element that is missing from that first test. The other element that is missing is that that's a fairly artificial test. It's just a dash speed test that has a lot of the amount of memory that it's accessing is fairly small, so it's really just accessing memory that is local. When you have a more complex application, then that's when you start having issues. When you have different phases in your application that might force delays in between the thread execution in different cores. And so some cores might be running essentially more, the thread in that core might be less busy than the thread in a different core, right? And that's when they always might start trying to move things around.
They're not professional, they're not really totally good balance unless I didn't know that the system itself.
So that's correct when you're not using MPI at all. If you're just doing threads and you let them float, you don't get a terrible performance. It's true. You can get I mean, the maximum difference you're going to get is a factor 2, and that only happens when you're doing things wrong purposefully. So now, once you put MPI in it, things change because the defaults for MPI are essentially put all the threads in the same place that the task was created. And so that's when you can start having problems with just the default. Now with this second example, what was your experience with the execution? Did you see any big differences here?
I haven't read the data yet.
Oh, okay.
I ran it, but I didn't digest the data yet.
Say that again?
I got
Done the other one. Yeah, so that's probably because, you know, the two options that you have there, NUMA control -L and NUMA control -I, all both of those are just handling memory policy. They're not handling task placement. So what NUMA control did was to put both tasks, one on each socket, and after that it enabled local memory policy. So that works much better than having the two tasks floating around amongst the 16 cores. And so probably what you're going to see here is you're going to see TACC affinity is going to go to the top. Then I don't remember how big this array is, but you probably see NUMA control either interleave or local first, and then no control options last. Yeah, and I showed them before some of it, and I told them that, you know, they should feel free to grab it and make any modifications if they want to play around with. Yeah, we had some cases where somebody needed to do things like have a different number of tasks on the first node that they're running and the other nodes, because the first node requires a lot more memory per task, for example, because it's doing all the I/O. I think that was a case that John helped with. And, you know, your code or your problem might require some other adjustment. TACC affinity is really just supposed to give you, both TACC affinity and Ivy run, they're just supposed to give something that is good overall for most people.
But we like you to understand what's going on with the top.
Yeah, well, and the next one is just to repeat a few times and see, and you should see that when you take the average of this, you will see something fairly consistent, which is the using TACC affinity with that evenly distributed tasks to the two sockets and local memory access preferred on those sockets is going to give you the best performance for this particular case. And this particular case, like I said, is very simple because there only is a phase to this execution. It's just doing the 2-vector multiply. So it's not really something very complex. There's no change in what the code is doing at all. But yeah, the most important thing to remember is, particularly if you're using the Mbappage2 library as part of your execution, that you want to make sure that you put in TACC affinity. Because the Intel NPI library is much more clever about designing things in runtime, and the defaults work pretty well. But Mbappage2 has, for some reason, and I think the reason is that when they started developing it, hybrid was less important than it is right now. They took a lot less care of of task placement for hybrid codes. And that's pretty much all I had. You have my email on the slide, so if you have any questions regarding this or anything else at TACC, just feel free to send me a line. I'm typically responsive. And thanks for your attention. We're going to break now for lunch. And Jason, what time are we going to come back? Around 1? Or? Yeah, we finished earlier than the schedule says because this lab is pretty straightforward.
You can stop the broadcast.